Hi, everyone, and thanks for joining me today for episode 825 of the People Behind the Science podcast. We are revisiting our conversation today with Dr. Zach Eilon. Listeners, Zach studies the Earth's tectonics, including how continents are built, how they break apart, and what's going on under the Earth's surface beneath the ocean floor. He wants to know how tectonic plates move and interact with each other. And to answer his questions, he uses data collected on the energy released during earthquakes. This energy picks up different signals on its way through the Earth, and Zach creates computer programs to interpret those signals and produce snapshots of what's occurring inside the Earth. He shares more about his fascinating research, his life, and his career in our interview. So I hope you are ready to learn more in this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to People Behind the Science. Today, I am thrilled to introduce you all to Dr. Zach Eilon. So, Zach, welcome to our show. How are you today?
I'm doing very well. Nice to talk to you today.
Fantastic. Well, it is a pleasure to have you here with us today, and we are excited to learn more about your life and science. But before we dive in, let me introduce you briefly to our listeners. So listeners, Zach is an assistant professor in the Department of Earth Science at the University of California, Santa Barbara. He is also conducting research at Brown University. Zach hails from the United Kingdom, where he completed his undergraduate and master's degrees in natural sciences at the University of Cambridge. Afterwards, he was awarded the Herchel Smith Scholarship to attend Harvard University for a year for a special studentship. Zach next received his MPhil and PhD in Seismology from Columbia University. He recently completed his position as a Postdoctoral Research Associate at Brown University. And listeners, Zach has joined us today to talk about his experiences in life and science. So Zach, today we want to get to know you both as a scientist and also as a person. So can you start by telling us what you like to do when you're not doing science?
Well, aside from always thinking about science, which is sort of plagues one, especially when you have research problems that you're always sort of turning them over. But to keep myself happy, I spend lots of time seeing friends, spending as much time as I can with my wife, generally on the internet, looking at houses we can't really afford. And sort of personally, I do lots of running. I'm quite an avid runner. I recently did my first marathon, which was a huge amount of fun and a huge amount of pain.
Congrats.
But I'm kind of excited to do another one. Yeah, it was all going very well until one of my legs just stopped working.
Oh, no.
Which is a rather remarkable experience, about 5 miles from the end. So it was a process of sort of crawling my way to the end, which was exciting.
Yeah.
I do a lot of cooking as well. I actually love to cook. And while I'm doing almost everything, I'm listening to podcasts. So it's sort of exciting to be on the delivery end of one of these because I spend something like 5 hours a day listening to podcasts as I'm pottering around the house.
Oh, wow. That's impressive. So do you have a favorite?
Oh, several. I'm quite into the political podcasts at the moment and some comedy podcasts. I mean, I listen to all the Pod Save America family. On the more lighthearted side, I like mostly the Gimlet podcasts, and then some great history ones. History on Fire is excellent, as well as, of course, Hardcore History with Dan Carlin and sort of classics. I often sort of extol the virtue of podcasts to people and then end up sending them a list of something like 20 that I recommend.
You overwhelm them with your recommendations.
Yes, exactly.
Oh, that's wonderful.
Most people don't have the commitment to sit through all of them at 1.5 times speed as I'm now having to do.
So you also mentioned an interest in perusing houses.
Oh, yeah, absolutely.
Are you guys looking on the market?
Well, we are because we're moving across the country. We're about to leave New York and move to Santa Barbara, where I will start my assistant professorship. So we're sort of excitedly looking at all the places that we could never possibly move into.
Of course, of course. It's always good to dream big.
It's always good to dream big, absolutely. Or at least dream 3-bedroom or something.
Right. So, Zach, it's wonderful to hear more about your life outside of science, but I do want to chat a bit about your scientific side next. So can you tell us how you describe what you do to someone who might not at all be familiar with your field?
So it's always a slightly fraught experience when I'm at a dinner party or something and someone says, so what do you do? It's difficult to know where to start. What I generally say is something like earthquakes, because that's really gets people's attention and is an exciting thing to study. But really what I do in my day-to-day job is I write computer programs that take pictures of the inside of the Earth, right? I'm interested in the tectonic problems. So how do continents get built and how do they break apart and what's going on beneath the surface of the oceans? And in terms of the oceans, I don't mean sort of the bit with the water on, which is for hard rock scientists is a bit of an inconvenience. I'm talking about beneath the rocks at the ocean floor, what's underneath that, and how the tectonic plates made, how do they move around, how do they interact with each other. And earthquakes are really the way that we probe the interior of the Earth. So there are two kinds of seismologists, which is the word for an earthquake scientist. One kind studies sort of why earthquakes happen and how they happen and what the source processes are and what happens when bits of rock rub against each other and when they release the energy that they're storing. And that's not me. So the other kind of seismologist, which is the kind that I am, we sort of make the best of a dangerous process and use the fact that the Earth is constantly releasing all this energy, which then propagates through the Earth's interior. And as it passes through the rocks within the Earth, it picks up various signals. And so it's my job to interpret those signals when we receive those waves at the Earth's surface on our very sensitive measuring instruments, and essentially use them to do something like a CAT scan of the Earth's interior. So a CAT scan is a pretty good analogy for how we take those pictures that I mentioned of the inside of the Earth. Because as the earthquake goes through, it sort of takes a snapshot of the structure inside the Earth. And just like with the CAT scan, you have some sources that spin around let's say you're scanning your head, right? We're not going to cut into your head because that would be painful and dangerous.
Right. A bad time.
Exactly. So we sort of send energy through it. And you have a series of sources on one side and receivers on the other side. And it propagates the energy through your head. And along the way, small bits of that energy are absorbed or reflected or things like that. And you do this lots of times in lots of different orientations. And by looking at different amounts of absorption of that energy at different angles, you can sort of build up a 2D or a 3D image of the volume within your head, which is more or less absorbing. And then it's the job of doctors to relate more or less absorbing to, well, this is this tissue and this is that tissue. And this means that you have no problem, or this means that unfortunately there's something wrong with you. And what we do is relate the propagation of those seismic waves as they go from the sources, which are the earthquakes, to the receivers, which are what we distribute over the Earth's surface. And we're doing so more and more. And we relate those to heterogeneities within the Earth that we ascribe to, here it's much, much hotter. And here there must be some molten material trapped within the Earth. And here we think that you've gone from one rock type to a completely different rock type. And that tells us that these two great continents crashed together 40 million years ago. And that's what's juxtaposed these different rock types. And we can see that there are differences because as the earthquakes pass through that region of the Earth's interior, they change character in some way. So that's really what we do.
Very cool.
Yeah, that's kind of the slightly longer answer. And by this time, the people at the cocktail party have all turned around.
They're trying to slowly back away from you now.
Exactly, slowly backing away, going back to the bar for another drink. But the few that remain really enjoy it.
Well, Zach, wonderful to hear more about your work. And I love all the analogies that you use in there to really make it accessible. And I think as you're doing your work, there's so much to get done in a day that it can be hard to stay motivated. But I love talking to scientists about what motivates them. So do you have something that really motivates you? Or do you have a favorite quote or a saying that you can share with us to keep us motivated?
Well, in terms of motivation, I think just sort of the problems that we're trying to tackle and all the small puzzles that we're trying to solve, I find them fairly self-motivating. So I don't really have troubles with that sort of thing. In terms of a favorite quote, I actually really like a quote which I think is attributed to Einstein, but I'm not sure if he actually said it. I knew I'd be talking about this. I looked it up just to make sure, and apparently the provenance is uncertain.
It is disputed, yeah.
Exactly. But the quote is, make everything as simple as possible and no simpler, which is actually, I think, a great piece of advice in life in general, but also sort of specifically within the kind of science that I do is actually very, very pertinent, because the real skill and talent and art of the sorts of science that I do, the sort of pictures that we try and make of the Earth's interior, lies in our ability to determine exactly what our data require and no more. And this speaks to a branch of sort of scientific mathematics, which I use a lot, which has a fancy name. It's called inverse theory. So the name is unnecessarily scary, perhaps, because it's really very simple. It's just about, you have a bunch of data, right? You've made a bunch of observations. Now, what can you tell from them? And it turns out there are various formal, rigorous mathematical ways of working out exactly what you can tell from them. But of course, within any measurement that you make in any science, especially in the earth sciences where we have lots of noisy stuff going on that is interrupting our senses. So all of the data measurements that we make contain some noise, right? So you could devise some model of the Earth that fit every single little wiggle in your data stream, but you would be fitting a whole lot of that noise. So the challenge is to make your model as simple as possible. So to try and get rid of all the extraneous information that comes from all that noise, but no simpler, because you don't want to overly simplify this thing to capture only the very, very coarsest information that's in your data. there's this delicate balance between how much you should believe your data, how much you should try and fit it, and what sort of assumptions that you make when you're constructing your idea about whatever model it is you're trying to obtain. So it's a very instructive quote, and it really sort of describes, in some ways, the project of science, and make everything as simple as possible, get down really to the fundamentals, but no simpler. There are some things that really are robustly complicated, and we want to describe those as well.
Absolutely. Well, I think it's so critical for communicating your science as well to keep it simple, have a main message, but don't overwhelm people. Yeah.
Absolutely. Yeah.
I love it. Well, wonderful quote. Now, I'm curious to hear a little bit more about who might have motivated or inspired you along your journey, Zach. So do you have some mentors or role models who you can really point to who had a big impact on you?
I've worked with lots of wonderful academics during my career, but I think the role models I've had, I suppose, come from my family. There's a very unusual situation, actually, that my family is extremely academic. My dad has a PhD and his dad was a professor. I have several aunts and uncles who have PhDs. One is in the sciences. My other grandma is also a professor. So I sort of had a very fortunate experience and continue to do so within my academic career in terms of having these role models that just seemed like normal people whom I love because they happen to be my family, but who are academics. And so I was in this sort of unusual position, really always feeling like I belonged in an academic setting. And this definitely caused me to reflect on the importance of your background and the sort of the small advantages that come along with the sorts of privileges, such as coming from an academic family, because I'm aware that peers of mine, and I'm sure that future students, etc., of mine, will not necessarily come from that sort of background. Lots of people are the first to go to university and things like that. And absolutely more power to them. And the fact that the university setting and the trappings of that sort of lifestyle don't come naturally to some people and seem foreign and are foreign because they don't have sort of a lineage of this is a real problem. And it's something that we have to overcome. And so I'm quite conscious that the role models that I have that just sort of normalize the idea of, yeah, of course, you can absolutely get a PhD. It's no problem.
Right.
If you just work hard enough, you can do that. That's not available for lots of people. And the idea that it's a perfectly viable lifestyle to be a professor, I'm sure lots of people don't start off with anything like that premise. So I think it's an important thing to think about.
Definitely. So for you, was there a lot of pressure to pursue this lifestyle then, coming from a quite academic family?
Not really. I mean, no one ever expected me to be an academic at all. I was always sort of expected to pursue schoolwork and things like that seriously because that's what we did. So again, it's sort of just setting those expectations completely differently makes a big difference. But no, I think my parents would have been, and my family would have been happy whatever I did. But of course, they were very supportive, and the early stages of my career were very helpful in doing things like writing personal statements and things like that because they sort of knew that world. With the exception of my grandpa, none of my family is remotely interested in the sciences. So once I got beyond a certain stage, they were really very unhelpful.
Right. So now can you tell us where this interest in science began if it was not necessarily coming from your family?
I had always sort of loved maths and physics. I think this is a totally alien concept to people that don't sort of get it and a totally familiar one to those who do. But yeah, maths is such an elegant way of describing problems and describing the world. And physics was always totally intriguing to me. And actually, so I went to university, to Cambridge, intending to study physics. And like hundreds of other people every year, discovered that once you get to the university level, physics is not for everyone. One of the great things about the Cambridge Natural Sciences course is that unlike the other, I guess what you'd call majors, to translate to the American audience, unlike the other majors in the UK, the Cambridge Natural Science course allows you to take several subjects in your first year. So if I'd gone to somewhere like Manchester or other places where I'd applied, I would have done something like physics, and then I would have been in that track and fine. But in the natural sciences, you have to choose 4 different courses in your first year. So I chose physics because that's what I knew I wanted to do, and also maths. And then for fun, I did evolution and behavior, which is an absolutely fascinating course. And then I was signed up for material science and metallurgy. And I went to the first lecture, and it was not for me, should we say.
Fair.
But my friend had just come out of a geology lecture and said, that was brilliant. You should come along to the next one. So I went along to the next geology lecture, and the first 8 geology lectures of the first year, the department puts up I think he's still the head of department, maybe he's transitioned. It was the head of department then, a very gifted lecturer called James Jackson, who's also a wonderful seismologist. And his early lectures are there to get people hooked. He just made the Earth sound incredibly interesting. He had lots of sort of fun gimmicks. Like I remember in one of the early lectures, he picked up this boulder that was sitting on his desk at the front of the lecture theatre, and he hurled it at a student. So everyone went, oh! And actually it was this very big thing, the size of a basketball or something, but it was pumice. So it was light as a feather.
Ah, lightly bounced off, yeah.
Exactly. This is a big rock. Why is this so low density? Why is this full of air? It's like, why is it full of air? That's an interesting question. So he had little hooks like that, which really got me interested. And then the clincher was various department field trips to go out to various islands in Scotland and do some mapping of the rocks. And I was clambering around on some mountainside for work with my tools at my side and noting down the various morphology of the rocks there and in the Scottish countryside, and sort of looked up and this is brilliant. This is exactly the sort of work I want to be doing.
Right.
And then I gradually circled back within earth sciences back towards the physicsy side of things, because that's where I really enjoy the mathematical problems. And so now I go out into the field as much as I can, but in order to gather seismic data. And then I do lots of programming and data processing and things like that in order to, as I mentioned before, turn that into pictures of the Earth's interior in places that we can never access physically. We're not going to be able to drill into these places. We're definitely not going to be able to dig down to them or touch or put our finger on them in any other way. So we sort of take what we can from these signals of the Earth's interior and we combine those with the people clambering around on the mountains of the Scottish Highlands and sort of ally the two to understand what's happening in the interior and through time. And that's sort of the full circle of how I got to where I am. And it's kind of funny how people find their way into the earth sciences. I think if you did a poll of scientists, most of them would not have imagined themselves as scientists when they were growing up.
Mm-hmm.
But people who are in it love it because it's such a tactile discipline. We can really go out and see and touch the things that we're studying. And that's really exciting.
Absolutely. Well, wonderful to hear more about your career path. And then I know you had an opportunity in graduate school to then actually come to the United States for this 1-year experience at Harvard. Can you tell us what that was like?
That's right. That was fun. It was a bit of an academic gap year. It was a non-degree program, so I didn't have to really worry about grades or anything or fulfilling requirements or anything. I really got to do what I wanted. So I split my time between doing some courses in the science department with some wonderful, wonderful people there, and they were very interesting and useful for the future. And then the other half of my time I spent doing courses that were just incredibly interesting. So one of the ones, I'm trying to think, I did the stereotypical course called Justice, which is about sort of moral philosophy. And yeah, I guess the history of moral philosophy and how it determines how we should think about it within society. And that's like a 1,000-person class or something. Everyone takes that. But
oh, wow.
I thought that this is cool.
Yeah.
So I turned up for that. I did another one called Religion and Existentialism. I did Gender, Sex and Evolution. So I just sort of did things that I thought seemed fascinating because, like I said, in the UK university system, we don't really have the chance to do things like a liberal arts education. So you never get to do those slightly random courses that just fascinate you, but that don't have much to do with your eventual career path or your academic major. So this was sort of my opportunity to do some of that, and I loved it.
Now, can you tell us then how you decided to come to Columbia University for your PhD?
I suppose I applied and I really liked the sound of the people there and the projects that I could work on there. And so having been fortunate enough to be accepted, I decided to go there.
Excellent. It made the decision easy.
Well, no, it wasn't that easy. I was also sort of in the middle of a two-body problem with my now wife, then girlfriend. So we were sort of deciding between cities. And so New York also had a lot to offer that some other places didn't. We had a spreadsheet and we had the pros and cons of various places, and Columbia rose to the top quite easily.
Fantastic. And then you were able to solve the two-body problem again when you were working on your postdoc at Brown?
The way I solve it is by doing a lot of driving.
Okay.
My wife is finishing her 4th year of medical school here in New York City. So we live here and I spend the weekends here and the weeks up in Providence.
Gotcha. And now the next position, the next big thing that you're about to embark on is this assistant professorship at the University of California, Santa Barbara. Are you ready for it?
Yes, I think so. I suppose one never knows exactly what to expect in a new position and moving to a new place, but the department is lovely and incredibly friendly and the people are great and the place is wonderful. And I'm really excited about the opportunities for science there because I feel like it's a bit of a blank slate. Up to this point, I've always been working in collaboration with mentors. So I certainly have input into the things that I'm studying, but not exactly full autonomy. So now the opportunity to really branch out and do my own thing is what I'm really relishing. And I'm also really looking forward to teaching, actually. I enjoy teaching a lot. So you can check back in with me once I've taught my first 300-person freshman class. But
right. With the pile of people that come afterwards with all the questions. And yeah.
Exactly. So we'll see how that all pans out. But I like getting up in front of people and spouting off about why the Earth is interesting, as perhaps you can tell.
Wonderful. Well, great to hear about how you got to where you are today. But Zach, I think we want to hear a little bit more about what you're working on right now. So is there one project you have in progress that you are just so excited about that you want to tell us about?
Sure. Well, the project that I've been spending most of my postdoctoral time on is devising a new algorithm a new method for looking at how the continents were built and how they break apart by allying different types of seismic data. There's this new methodology which is coming into vogue in the earth sciences because suddenly we have more data than we've really had before. I mean, it's been accumulating over the last few years and decades, but we really have more data than ever before, almost by definition, because if we leave these things out for every year that passes, we have a bit more data, and it's very useful. And we also have more and more computing power that we 10 years ago just didn't really have access to. So what's becoming increasingly common and increasingly exciting is a set of algorithms that rely on Bayes theory to turn the few measurements that you have into a whole ensemble, a whole suite of possible Earth models. And you try a bunch of these things. And because you have big computing power, you can try many more than just sort of trying to look for your single favorite model. So instead, you come up with an enormous suite of thousands and thousands of possible models that could explain your data. And then you have various statistical ways of deciding which ones are good and which ones aren't so good. And what you come up with is a range of possible things that could actually explain what you're seeing. Because there's this tricky thing. We really only see a small part of the Earth. We get these infrequent earthquakes that illuminate things once from one angle or something, right? So really our data don't contain enough information to tell us everything. And so we understand the physics of the Earth's interior pretty well. We understand how things like the waves propagate through and across and over the top of the Earth. But we can show through the sorts of work that I'm doing that there are actually lots and lots of possible Earths that could exist beneath our feet. And I'm not talking about sort of the really big scale stuff we know very, very well. It's not the sort of multiverse of possible Earths we could be living on. No, we know pretty well what's down there. But in the details, it turns out there are lots and lots of possible alternatives around the edges of our understanding. The project I'm working on is a project which sort of throws all that into a big algorithm and tries to work out using many, many different data types. So different kinds of waves that propagate in different directions and with different sensitivities, and throws them all together and tries to come up with the ensemble of possible models that could explain the data. From that ensemble, we can pick out, well, we think this is the most likely kind of Earth that we're sitting on right here. We think the top layer is this thick, it's this temperature, and it means we have maybe this much melt in the interior or this or whatever. But it also gives us uncertainty bounds on that preferred model. And that's something which is actually really difficult. And this speaks to one of the problems that has been surfacing in the science as a whole in recent years, which is things like reproducibility difficulties and being really robust about the uncertainties in your findings. Because like I said before, all data have noise. So whatever answer you come up with in whatever scientific field you're really looking at has some uncertainty to it. So we're really bad at estimating that uncertainty, right? So I will tell you my favorite model, and then I'll say it's plus or minus something. But actually that something is pretty poorly known. So this is all sort of a long way of saying this current project does a really good job of coming up not only with a really good model that does fit the data, but also really very robust bounds on that uncertainty. So I can tell you both what I do know and what I know I don't know, to go sort of a bit towards the Donald Rumsfeld known unknowns. Right. Which is a super important part of the sciences, because we have to be really upfront and knowledgeable about the things that we don't know and that we can't quite get to. And we might not be able to get to them because of a limitation in our theory, but more often in my field, it's because of a limitation in the data that we have available to us.
Absolutely. And I know you're doing some work with faults in parts of the Earth that are deep under the ocean. So I can imagine it's really hard to see what the Earth looks like when you're talking about.
It's super hard. Yeah, exactly. Yeah. Some of the measurements that we make literally hundreds and hundreds of kilometers away from the thing that we're measuring. And there's obviously a lot of complicated stuff between that point and the sensor. So it's difficult. I suppose astronomers have something like this because they have to make these measurements at an extreme distance. But speaking almost wholly in ignorance, I think that the signals between distant stars and observing them at our telescopes, for example, those signals aren't perturbed too much. I imagine there are various ways that they could be, and I really don't know very much about it. But I think they're not perturbed too much, whereas in the Earth, there's some signal from a particular feature 300 kilometers down into the Earth. And then it's got 300 more kilometers of weird rock to go through before it gets to our sensors.
Right. Distorted in ways you can't understand. Yeah.
Exactly. So it's a super difficult thing to do, but we're getting better and better at it. And it's exciting because it's the stuff we're walking around on, whether we're walking around immediately on top of it or a few kilometers on top of it. It's right beneath our feet, which is kind of weird and wonderful.
Absolutely. So on the topic of problems, I know science is fraught with problems and people might not be aware of them because what they often see at the end is just sort of the beautiful big picture, whatever we're able to publish and get out there. So I love talking about the challenges and struggles of scientists. So Zach, do you have another story of a challenge or a problem or maybe a major failure that you've had that you'd like to share with our listeners today?
I suppose I've had a short and lucky enough career that I haven't had yet, touch wood, any major failures. But I think the struggles are every day. You're trying to write some program and it's just not giving you what you want, right? Something is either failing or your computer keeps telling you to go away. Right. Or the data, I've got a great idea to pull this signal out of the data. You spend an hour on it and absolutely nothing. So I think the struggles all the time. Some of the biggest struggles are also deadlines. A certain proposal has to be due in by a date, or you have to revise a paper and give it back to the journal to look over again by a certain date. And so those are sort of the most stressful times and some of the toughest struggles, but at least they're blessedly finite by that date.
Right. You can sleep afterwards. Yeah.
You can sleep afterwards, yeah. But yeah, I don't really have sorry to disappoint, but I don't really have everything went wrong and my computer died. So one of the things I'm getting into in the near future is, as you said, instrumenting more of the ocean floors. So the way we do this is we sail out into the middle of the oceans or wherever, and we throw these instruments off the side that are called ocean bottom seismometers, and they sink to the ocean floor and then they stay there recording free. It's an amazing process that we send these things over the side of our ship and they float down a few miles to the ocean floor and they sit there recording. They deploy the little instrument and the instrument couples into the earth and then it detects vibrations across the other side of the world. And then you go back in a year and you send a signal to them. And if they're working and if their battery hasn't died, then upon receiving the signal, they send a little current through a wire, which is attaching the instrument to a concrete base, which is keeping it to the bottom. And the current going through the wire causes the salt water to electrolyze the wire and it burns through it. And so it cuts their connection to the weight. And so they float up to the surface and you pull them out. So it's an amazing, amazing technology. But to the subject of sort of enormous failures, I am aware of previous experiments that some of my collaborators have actually been involved in, where you send the signal to these things. Each of them costs tens of thousands of dollars, and over the course of the year has hopefully been recording fabulous data. And you send the signal to them and you hear nothing.
Oh no.
And you circle around in your ship a bit and you send your signal and you hear nothing. And eventually you just have to leave because they're dead or whatever. And sometimes you'll deploy 30 of these on the ocean floor and you'll sail around trying to pick them up a year later and you'll get maybe 15 of them back.
Oh, wow.
We're getting much, much better at getting them all back. Recent experiments have had 95% recovery rate, but there are always some spectacular failures. There was one recently where we could hear the instrument. It was chirping back to us, right? We send these sound chirps back and forth between the instrument and the boat. And it was chirping back to us and it wasn't moving. Mm-hmm. And later we found out that it had been trapped in a lava flow at the bottom of the ocean.
Oh, no.
Yeah. So this lava flow had swept over it. And so it was, I don't really know how to think about it. It must have been poking out of the top of the flow.
Just a little bit. Yeah.
But its feet were somehow stuck in the newly hardened rock. So that wasn't coming back ever.
Right. That's down there for good. Yeah.
That's down there for good. So yeah, fieldwork always brings its fantastic share of failures.
Well, I love these stories of challenges and perhaps preparing yourself for the upcoming challenges that are about to go down. And I think there are absolutely these things that people just don't even think about. Like you never would have imagined starting the experiment that your sensor would be trapped in lava at the bottom of the ocean because
exactly.
There's no way to prepare for that.
Absolutely. And you see the things that are growing on them when we bring them back up.
I bet.
It turns out half the earthquakes that we see are just octopus housing.
Wiggling it around a little bit.
Yeah. No, we generally get very, very good data out of them, actually. It's kind of amazing that it's so good considering the things they go through.
Absolutely. So great to hear about the challenges, but I do want to talk about the successes next. So Zach, do you have a story of success that you can share with us today?
Well, I suppose one of the recent successes that I have had was in the work that I did last year, actually using data from these ocean bottom instruments, which, like I said, now come up more often than not, which is helpful. Mm-hmm. So the community got together and the community of lots of academic institutions and helped by government agencies and deployed a fleet of these things across the Juan de Fuca plate, which is a small tectonic plate just off the northwest of the US. It goes up from Cape Mendocino in California all the way up to Vancouver Island in Canada, actually. We put these instruments down across the entire plate. And so that was just absolutely amazing new data set. We've never had the ability to see an entire oceanic tectonic plate before, but we now did. So I took that data and I came up with a slightly new and improved and fancy method of analyzing a certain phenomenon that was recorded within that data. This phenomenon is called seismic attenuation. It's the rate at which seismic waves lose their energy. And it's basically related to how squishy the Earth is. If the Earth is a lot squishier in its interior, then the energy dies out faster. And if it's very hard and competent in its interior, then the energy propagates much further without losing energy. So I came up with this new method of measuring this property, and I applied it to this completely new data set that no one had ever had access to before. And we saw something kind of remarkable. We saw basically the strongest signal of this attenuation, this energy loss rate, basically ever seen anywhere on the planet. And it told us new things about what's called the mid-ocean ridge, which is where this little microplate is separating from the big Pacific tectonic plate, which underlies most of the Pacific Ocean. And where the two separate is actually where new plate is formed as hot rock sort of wells up from the Earth's interior and then solidifies on both sides and produces the plates. And this is going on all over the planet. And this is one of the first times that we've had the ability to look at it. And so it's kind of unsurprising, but still the strength of it was kind of surprising how strong a signal of this attenuation that we saw beneath this region. And what it told us is there's probably a lot of molten rock trapped within small sort of pore spaces, little pockets of melt within the hot upwelling rock, way deeper than we thought. It kind of challenges some of the ideas that we've had about this process of the mid-ocean ridge process, I guess, where these new plates are formed. And so this is one of the fundamental tectonic processes on the planet. And by looking at it in a slightly different way, and most importantly, with this phenomenal new data set, we came up with some results that really change how we have to think about what's going on down there, which is kind of nice.
Congratulations on these exciting findings. And I have to ask, as you saw these results starting to come together, what was going through your mind?
I was like, oh dear, this is far too strong a signal.
Yeah.
That's really what goes through your mind. If you ever see something new, you have to be super careful about it, because you have to try and convince yourself that you've not simply made some mistake, or you're overinterpreting something, or you've made some mistake in the coding or anything like that. So as these results are coming in and I'm looking at these things like, well, the signal is amazingly strong. It's very consistent and it really looks like it should, but it's way too strong. No one's ever seen something quite this strong in somewhere like this. So we did a lot of work to convince ourselves and then also to convince the reviewers of the manuscript that we published on it that it was a real signal, but it does appear to be. And so it's very difficult to escape the conclusions that we came up with. So it's a mixture, as you're seeing these results, of sort of excitement and also, oh, wow, that's worrying.
That's something. Yeah. Right. Well, fantastic to hear about one of these successes, and congratulations again. And I know in doing your research, you have to sort of be mired in the literature, always reading things, always staying up to speed there. But I do like to talk to scientists about what they're reading outside of the scientific literature for a bit. So do you have a favorite book that you could recommend that you've really enjoyed? And it can be a science book or a non-science book.
A book that I read recently, which I really enjoyed, was called The Silk Roads by a guy called Peter Frankopan, I think. And it's a history of Central Asia and the trade routes through Asia over the last 3,000 years, and how in many ways they have dominated almost every country across the world's history in one way or another, more or less removed. And so totally fascinating to learn about that part of the world and its ramifications for the rest of the world. And another one which I absolutely love and always recommend to people, which is kind of in the same vein of, and speaks to my interest in geopolitics, I suppose, is a book called The Prize by Daniel Yergin, which is a book about the history of oil over the last 150 or so years and how it has completely changed global geopolitics. And he does this masterful job of not only telling wonderful small stories along the way, various oil finds and the personal stories of people sort of developing oil plays in the Arabian Peninsula and how it's totally idiosyncratic where they happen to go and how they were going to quit that day and they didn't quit that day. And then on that day, they found this enormous gusher of oil or something that changed the world. So he sort of weaves those personal small stories together with these grandiose, or grand, I suppose, explanations of how the strategic resource of oil affects all these decisions during war and during peace and economies. And yeah, it's totally fascinating. Lots of my friends have gone from PhDs in seismology, where we make pictures of the Earth's interior, to oil research, working for companies like Shell and ConocoPhillips and things like that in order to make pictures of the Earth's interior, specifically of the very shallow interior, to try and look for where there might be hydrocarbon resources. So I'd never really thought about that as a career path, but it's in the same world as that within which I now move. So it's kind of interesting on two levels for me.
Very cool. Well, great recommendations. I'll put these on our website for our listeners to find there. And I think throughout our discussion today, Zach, we've talked about some of the different places that you've been able to travel and all the different places you've trained, some of these opportunities you've had to do your research going out in the middle of the ocean. And I think travel is a huge part of the life of a scientist. So do you have a favorite place where science has taken you?
I think the best field work that I've done was probably in the northern volcanic zone of Iceland. where we were deploying an array of seismometers, of these seismic ground listening instruments. And we're really off the beaten path. So I've been to Iceland a couple of times and it's wonderful, great food and things like that. But to really see it, you have to get a 4-wheel drive and go right into the middle of the island where no one goes. And it's wild landscapes and brutal conditions. Our job was basically to go into the middle of nowhere and scatter these instruments in this predefined grid. And this entailed driving as far as we could and then hiking into very remote spots, digging holes, putting these instruments in the ground and leveling them. And then we had to build a little solar panel array to keep them going through the winter because they need power. And then we were logging these 100-pound batteries across these lava fields, which is probably the most dangerous thing I've ever done.
Oh my gosh.
I don't know if you've ever been to a fresh lava field or a reasonably fresh lava field.
I have not.
You're basically walking across the surface of the moon, first of all. I mean, it's literally where people trained before going on for moon landings.
Really? I didn't know that.
I've been told. I haven't checked that actually. But
yeah.
The lunar mares are made of the same stuff, right? So you're walking across this black, jagged rock, which is incredibly hard. I mean, I had to throw away my shoes after that trip because they were cut up. And these are like hard hiking boots.
Oh, geez.
And so you're walking across the top of these lava fields, and every so often, as the lava sort of flows, it will make these little tubes where a little jet of lava flows through a little tube, but then leaves it hollow. So every so often as you walk across these fields, your foot will crash through, sort of a foot's worth of, you're just walking across a little shell of a tube.
A little hollow. Yeah.
Exactly. And your foot crashes through into it and suddenly you're knee deep into jagged rock.
Oh no, carrying a 100-pound battery, right?
With a 100-pound battery. Yeah. So that was kind of a miracle that we all came out of that okay, but we did. But yeah, that was incredible. Just looking at the fresh lava is amazing. I've actually never been to somewhere like Hawaii or other places around the world where you can watch it pour out. But this was a pretty remarkable experience.
Well, this sounds like a phenomenal experience. And I think sharing some of these phenomenal experiences with your colleagues also adds to the fun. And I love talking about sort of this human side of science, because I think a lot of people think of scientists as very serious and sort of sitting in this austere lab environment. And that's really not the reality of life as a scientist. So, Zach, do you have a story of kind of the human side of science, some of these quirky traditions, these fun memories that you shared with colleagues?
In terms of a strange tradition, in the Seismology group at Columbia University, where I spent 5 extremely happy years, has this tradition every week of something called record reading, where we pick an earthquake that happened around the world from that week, or if it's been a slow week, maybe a previous week. And all the students and lots of the faculty and the research scientists get together in one room and talk about the earthquake and look at where it was, why it was there, what tectonically is happening, whether it's like the convergence of different plates or the bending of one plate as it slides into the earth or something like that, and the history of earthquakes in that area. And then we actually pull out the records. That's why we call it record reading. So we pull out the records of the instruments that recorded that earthquake. And it's a lot of fun, actually, to just get in a room, sort of be asking questions about, well, what's that little bit? Because we're looking at this series of records and you see, oh, there's a wiggle there. That's actually an interesting wiggle. Why is that wiggle there? And sort of the amount of attention a group of seismologists can pay to a couple of errant wiggles in a seismogram, right? One of these traces of ground motion is pretty hilarious.
Right.
And every so often you discover sort of interesting things. So like we've really seen systematically over the last couple of weeks that we've been doing this, there is this couple of unexplained things that seem to be present all over the earth. So what is that? That's not appearing in our predictions. So we should actually look into that. And then someone maybe that sort of sparks off a little research project or something like that.
Well, it sounds like a really good idea generator, just like you said, for new research projects and directions.
It is actually, yeah. It's fabulous.
So is this something you're going to continue in your lab then at UC?
Oh, absolutely. That's the first thing on the list.
Fantastic. Well, great to hear about one of these traditions you've experienced in your field. And I think as we're talking about your research, there are still so many unanswered questions in your field. And I think we're often constrained when we're doing research by things like funding, staff, technology, and feasibility. So Zach, if I gave you everything you needed today, what is the big research question that you would want to tackle first?
If I had everything that I needed to tackle it, I think I would probably try to answer why and when do earthquakes happen, which, as I mentioned earlier, is really not the kind of seismologist I am. Mm-hmm. But seeing as you've given me these magical powers, I think it's, for society's sake, it's probably good to try and understand this incredibly fundamental process. And I think one of the things that I would do if feasibility were not a problem, and this is actually being discussed tentatively among scientific groups, is trying to cause an earthquake in obviously an extremely remote location where no one will get hurt. If feasibility isn't a problem,
Then that place absolutely exists. Yep.
Yeah, exactly. Then we would try to induce an earthquake. And what we would do is we would put our measurement systems all over this area, right? Because the problem is earthquakes, we don't know where they're going to happen. And so we never have perfect instrumental coverage for when they do happen. So we always caught a little bit by surprise to some extent. But if you absolutely knew one was going to happen somewhere, then you distribute sensors all over the surface, and you drill boreholes and you put the sensors within the earth. So you were somehow able to image this entire thing happening in amazing detail and in 3D. And then you'd cause the earthquake to happen, and you'd see, so what actually happens to start an earthquake? Because we don't understand that very well at all, even though it's such a fundamental question. It's what we spend all our time on, these judderings of the earth, these earthquakes. But we don't really fully understand how they start or even why they stop, which is kind of remarkable.
Right. Which I've never thought of, but yeah, that's right.
Yeah. So we know in a gross sense why they happen, because they kind of need to happen because the earth is brittle and has friction.
There's a lot of pressure building up. Yeah.
There's frictional strength and there's pressure building up, and eventually it overcomes the strength. So it sort of goes. But at the moment we're reduced to, we can sort of fake these very, very little earthquakes by dragging or shoving a couple of small blocks past each other. And this, again, is not my field, and you should really talk to someone who knows about this stuff to a proper extent. But it would be kind of amazing if we could cause like a fully blown, real big earthquake, like a magnitude 5 or something, and watch what happens as the cascade of rupture starts to build up, and then as it stops, and try and work out why some earthquakes rupture all the way through things that look like barriers, and some stop at those barriers. It's kind of totally unexplained, but it has huge implications for seismic hazard and for seismic risk and places all over the world. If there were no limitations, that's the sort of thing that would be very cool to do.
Absolutely. Well, fantastic question for me and our listeners to ponder. And I know as you go through your scientific career, you are exposed to a lot of sources of advice, a lot of wonderful mentors. And I'm curious, Zach, is there one piece of advice that you received at some point during your career that you'd like to pass on to our listeners today?
Well, one good piece of advice which my old advisor gave me was essentially that the amount of time you spend on something does not translate to the amount of time that other people want to hear about it.
That is good advice.
So I think this does come into play in lots of arenas, but specifically if you're writing a paper about something and you've been cranking away on a research problem and it's taken you days and days and you finally crack it, that took a huge amount of effort. But in the end, describing the solution to that is maybe trivial. Whereas something else, which you just threw together in an hour and suddenly gave great results, that might be tremendously interesting and worthy of lots and lots of discussion and explication. And the fact that it only took you a small amount of time and the other one took you a long time doesn't mean that your paper should be mostly about the other one. Mm-hmm. That sounds very intuitive, but it's surprisingly difficult to adhere to because you know how much time you spent on that thing, right? You know how tough that one aspect was. And so you want to do it full justice, but a year later, you won't. And right. As soon as you publish it, no one else is going to care about the fact that it took you a long time.
This is true.
So you just let those things go.
Well, wonderful advice to share with our listeners. Zach, do you have any other last piece of advice you'd like to give them or a note of inspiration you'd like to leave them with?
Be excited about what you do because excitement is, I think, catching. And if you're interested in science or you're interested really in anything that you do, let your excitement about it show and try and tell other people, if they will listen long enough, try and tell them why it's so cool. And if you do that in a way that conveys your passion for it, they will be interested as well.
Well, I love this advice. And I think it's such good advice for scientists because I think oftentimes we're afraid to be overenthusiastic because we're worried it won't look as professional or people won't take us seriously. But I think that passion is critical to getting people excited about your work.
I totally agree.
Now, Zach, can you tell our listeners if they want to learn more about you and your work, where should they go?
Sure. They could go to my website, which is zeilon.squarespace.com. And they can always email me at eilon@ucsb.edu. That's EILON@ucsb.edu.
Well, listeners, definitely check out the website. Get in touch with Zach if you have any questions. And Zach, thank you so much for joining us to share a piece of your story.
It was a pleasure.
It was a delight to have you on, and listeners, wonderful to have you here as well. We'll see you next time on another episode of People Behind the Science. Your voyage to explore the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to chatting with you next time on People Behind the Science.